All right, let's get started. So I hope everyone had a good weekend. And so of course, just a reminder, we're doing our last lab this week. And so we might do checkout as well, but we'll kind of see how that goes. So of course, we're doing our ice cream lab. And then I don't know if people saw the announcement. Hopefully you did, and I apologize for the late notice. So I got an email on Friday saying that they wanted to come in and film and do like video of our classroom today. So same procedures, you know, if you don't want to be filmed, let me know and I'll let them know, and they'll avoid you. But otherwise, they want to see us do some fun, so we'll do our ice cream lab, so you can get the pickup and comparing our two methods of ice cream making. And then of course, poster presentation next week. And it sounds like everyone can come to the Thursday lab section. And to prepare those, if you need help, like I said, if you need help printing or just trying to figure out how to format or last minute, you know, questions, probably Friday would also be a good day to do that. What date is that? Sorry, I'm just trying to look at the date. Where are we? So May 30th. So May 30th, I'll be around on campus. Just email me though what time you can make it if you want to come. Like I said, I can help you print out your poster. Yeah.
Just a quick question about that. Does it have to be in that format, or can we just make our own poster board?
Yeah, you can just like make your own poster board too. So you don't have to use the template. That's just kind of a suggestion.
Okay.
But yeah, you could just like kind of piecemeal it together. And so that's kind of what I'm expecting is like, you know, you print out your papers, maybe tape them together, or, you know, if you can buy a $1 poster board, you can just tack them on there. And so again, if you want help with that, like printing anything, color printers, Friday would be a good time. And then we could also open up time on the Tuesday of week 10. So our usual lab time, so instead, right, we're not going to have any poster presentations that day. But if anyone wants to come in, so that's June 3rd, and do, again, any last minute printing or help or edits, I think those would be kind of good block session times to do that. So on Friday, I should be around campus around 11, but I can meet earlier if people need. Like I said, just shoot me an email so I know kind of how long to stay on campus. And yeah, same thing, right? So I don't know how late people need me to stay, but just shoot me an email and we can make sure that we connect there. And then, yeah, I should be giving y'all your final on Thursday, so you'll have hopefully plenty of time to do that. And so we'll say finals due on, I think that's June, yeah, June 6th ideally. And that can just go in the mailbox. And then the paper, I don't mind if that's submitted over email, but we probably want to get it in by June 12th would be ideal. So final paper, June 12th, and that can be emailed. Or I could always set up a Blackboard thing. Questions kind of sound good as we finish up. And so we'll be looking at our functional groups today, kind of finishing up our organic chemistry chapter. I still need to post the inner chapters, so I'll get the notes sorted out. And then the last week, so that's the polymer week and kind of a little bit of biochemistry. So we'll cover that. All right, questions, comments? All right, so let's look at our functional group chapter. So starting off, we're looking at alcohols, aldehydes, ketones. And again, right, we're just trying to appreciate and learn what we can. Obviously, right, your final exam is take home, so you don't have to worry about memorizing all of these. And that is typically what you'll have to do in organic chemistry, though, is of course memorize your functional groups. But again, we're just getting familiar with them in Gen Chem, kind of preparing for our next step. And so now we can recognize that an OH is an alcohol group. It's one of our functional groups. And so we'll see, again, our different naming. So we have methanol here, or methyl alcohol, again, as it's kind of like common name. And so with that, I just wanted to show you, so a couple of things. Well, now I have phenol pulled up, but as we continue going through these naming conventions, again, what we're going to find is, right, we have this IUPAC name that we're kind of being exposed to and trying to learn. But then there's also other variations of the IUPAC name, kind of depending on how you name it. And then, right, it also has all these other names, though, just for, in this case, phenol. And again, we're going to find that, right, for organic chemistry. There's a lot of different little naming variations that you can kind of run across. And so with that, I want to point out that we have this CAS number. And so this CAS number is a unique identifier. So it has an exact number that's actually associated with the compound, so that, right, when people are giving out all these different names of phenolic acid or phenic acid and you're trying to buy it, right, we want to make sure we can communicate, and especially internationally, right, since science is really an international discipline. So it gets confusing with all these naming conventions, so hence why we have this CAS number system. And so again, I'm just kind of showing you, so this is Sigma Aldrich, which is just a very common chemical supplier site. And if you were to just search phenol, well, you might get what you want. But again, you want to check it with your CAS number and not to be confused, right, with any other variations. So phenyl red. And so obviously different CAS number helps you figure out what is the same and what is not. And just for fun, that's the deuterated version of phenol. And again, I have a unique CAS number. And so same thing, so starting to look at the groups we'll focus on. So this is an aldehyde group, CO, and then it has H's, or really an H on one side. So this is kind of a more general aldehyde, where it could be connected to whatever hydrocarbon chain. And then shown here is methanol, kind of a strange IUPAC name. Most people just refer to it as formaldehyde, so obviously the simplest aldehyde. And then shown here is our ketone. So ketones have two R groups, so they're kind of sandwiched in the middle versus the terminal aldehyde. And so the simplest ketone is acetone here. So we'll keep, like I said, going through our naming conventions. And so we can start with our alcohols. And so we can see that they take the root of our hydrocarbon, and then we add our alcohol. So in this case, we're looking at methanol. And then there's no other positions, right, for this alcohol to be on. It doesn't matter where we attach the alcohol. It's always at the same position. Same thing with ethanol. So of course, ethanol, we can think back to ethane, obviously. So our 2-carbon hydrocarbon. And then ethanol, so again, just attaching one alcohol group to it. Doesn't matter which carbon, right? Symmetric birotation. And so now we start to get into a few variations. So drawn here, we have 1, 2, 3, so propanol, except this is 2-propanol. So telling us, right, what position our alcohol is attached to. And again, so now we're thinking back to priorities. In this case, it doesn't matter what priority we assign this carbon, right? 1, 2, 3, or 1, 2, 3. Either way, our alcohol is in the 2 position. And then does anybody recognize what this group is? We had named it like 2 weeks ago now in our hydrocarbon. It's also a common alcohol name. So this is our isopropyl group again. This weird little like 3-carbon chain thing. And then if the R group is our alcohol, so this is also known as isopropanol or rubbing alcohol. So that's our rubbing alcohol. And of course, I don't have it drawn on here, but we could draw out other variations. So obviously isopropanol is commonly used, but going with this propane chain, so 1, 2, 3, and then our alcohol, right? So now this is just propanol, or 1-propanol, right, if we want to specify, so at the 1 position. So again, pretty similar naming. And then of course this would continue, so we could go butanol, so 1, 2, 3, 4 carbons, and then an alcohol. And then again, right, always count again, 1, 2, 3, 4. And so that is 1 butanol there. So let's try, see if you can name this one. Kind of drew it a little funny. So this one has 2 names you could give it. So either the proper IUPAC name, or maybe you remember what this group is called. And so if you're in the chat, you can put your answer online too. So what are some names for this? Anybody remember what this little group is called? Kind of looks like the first letter of what it starts with too. So that is just a tert-butyl group. So this little, right, you have one carbon in the center of 3, and then it could be attached to something, or in this case, an alcohol. So this is commonly known as tert-butanol, or sometimes even just T-butanol if people are feeling really lazy. But we could have also tried to come up with its proper IUPAC name. So what's the longest chain that you see in this one? What did you say? 2. So 1, 2, but then, yeah, so 3. And it doesn't matter which way we go, right? 1, 2, 3. 1, 2, 3. Okay, it's still the same, and the alcohol is always on the same priority there. So now we have our propane backbone, right, of 1, 2, 3. And so again, just going back to our fundamentals, we can identify the groups on there. So we have a methyl group and an alcohol. So then the proper IUPAC name would be 2-methyl 2-propanol. So I'll write that that's the IUPAC kind of convention. Again, going with the IUPAC rules of identifying the longest chain and then naming our groups on there. Questions about those so far? And so then things can get weird, or at least they sound a little weird when we have multiple alcohols. So now let's practice that. So if I draw out this one, and so now we can put diol or triol, depending how many alcohols we have. So now let's again break down our IUPAC naming convention. So 1, 2, right? We just have ethane backbone. And okay, that also means that our alcohols are attached at the 1 and 2 position. So then this alcohol is 1, 2 ethane diol. At least that's its proper, again, IUPAC name. So this is commonly known as ethylene glycol, though. So again, even all these simple molecules have multiple names. And so now let's look at 3. So take a look at it for a second. What's our longest carbon chain? What do we see? So how many carbons is this? 3. And so again, it doesn't matter if we go 1, 2, 3 or 1, 2, 3, same priority. And so, okay, so 3, that means we have propane, and then we have alcohols on the 1, 2, and 3 position. So this is 1, 2, 3 propane and now it's triol to signify that we have 3 alcohol groups there. And so let's look at some alcohols and rings. So let's see if we can guess. What might this one be named? Do you remember what this 6-carbon backbone is called? What was this called? Do we remember that name? So benzene has the double bonds. So not benzene, but how many carbons are there? 6. So then, and it's a circle, right? So cyclohexane is at least the backbone. So that's this compound. And again, right, this is a good time to remind ourselves that cyclohexane is not to be confused with benzene. And so the whole point of cyclohexane is that it has a 3D structure. And so you'll look at this a lot more in OCHEM of what's called this chair and boat conformation. But again, all I'm trying to get you to appreciate is the 3D nature of cyclohexane. So it has, again, right, 3D shape does matter versus benzene, which is flat. And I can pull up a picture of benzene again. But again, this is where the hybridization helps us, right? So benzene has those alternating double bonds. sp2 hybridized, meaning it's flat, versus all of these. So all these are sp3 hybridized. So again, right, 3D structure kind of matters in that cyclohexane. All right, so then if this is cyclohexane, then this is cyclohexanol for the alcohol group. And so then if we add another substituent to it, so usually the alcohol should get the priority from the oxygen. So see if you can name this one. And I didn't mean to put, looks like I put stereochemistry. So then what number should be assigned for our methyl group here? But so the alcohol should get the 1 though, right? So then 1, but then we want to go, because you want to go keep the lowest numbers. So then 1. Yeah, so I'd go 1, 2, 3, 4, 5, 6. And so then you get 1 and 2. And then we don't need to specify necessarily the position that the alcohol's in. But then the proper IUPAC name then should be 2-methyl cyclohexanol. Questions about this one? So let's try another one. So kind of, this should remind you of your lab maybe. I'll draw. So identify your longest chain. So any guesses on the name? What's our longest chain to? That's a good start. What other groups are in there? So how many carbons do we count?
4.
So 4. So some sort of bute. But then what do we have here? So double bond. So now we're at some sort of butene. I may need to fix this. I'm just kind of sketching it out. And so again, right, just break it down. So okay, we have our 1, 2, 3, 4 carbon chain. And then, right, just like before, we want to assign priorities. So alcohol, we want to have a high priority. Same thing with our double bond. So that's going to be the best, right? We don't want to go 1, 2, 3, 4. Because then, right, our double bond would still have the 2, but then the alcohol would have the 4. So that's not really ideal. And then, all right, so we have our 2, we have our 1 position for the alcohol. And then how else do we need to describe this butene molecule? What do you remember about these groups? So alcohol, but then what else about them? Because remember, there's 2 different conformations. So not a 1. We'll put the 1 for the alcohol, but what else should we show here? It might help if I draw the other isomer. So what's the difference between these two?
Cis.
Yeah, so this one, we want to specify that it's cis. So then it'd be cis 2 butene, and then 1-ol is one way to write it. Or some people may even leave off the 1 because it might be assumed that the alcohol is the highest priority. Again, that's where the CAS convention helps so that there's not confusion. And then, yes, so then this would be the trans one. So again, right, we're emphasizing that you cannot have rotation around this double bond. So whatever conformation it's fixed in, it's fixed in. You would have to, chemically make a single bond and then remake a double bond or something to flip it. Questions on those? I just don't want to go too fast.
I had a question about the cyclohexane. So you didn't preface it with the ortho. Is that because it's not a benzene molecule, it's a carbon chain?
Yeah, correct. But so now, well, actually, I don't have an ortho one. But yeah, that's only for the aromatic chain, exactly. Just kind of confusing. And so then looking at a few more, so see if you remember what this one is. We looked at it earlier. So do we remember the common name for this one? Phenyl, yeah, good job. So phenyl, so that's again the common name. I think the proper IUPAC name would be to name our benzene ring, right? So it would be benzene then. And so again, just reminder that this is flat, sp2. And then, again, this is the one that I had showed in the beginning of class, phenyl here. And something that I want to point out is it is acidic. I don't know if you remember this from the acid-base chapter that we did. It was there in like the equilibrium table. But it's kind of weird that it's acidic since it doesn't have kind of the traditional carboxylic acid group, which we're going to look at in a second. But we can take some time to appreciate why it's an alcohol, or excuse me, an acid, a weak acid. And it has to do with this benzene ring here. And so this benzene ring is good at, again, right, stabilizing this charge so it can kind of distribute any sort of charge over the whole ring there. And so let's add, how does it function as an acid? So kind of the question that you can be thinking about in your mind is, why is phenol a weak acid versus like ethanol would not really be considered acidic. And so we have to, again, kind of compare the protonated structure versus deprotonation, right? So minus an H now, if it's acting as an acid. So just definition of an acid. And so then we get this, right, negative charge on our oxygen, which is, you know, it's not the greatest. I mean, yes, oxygen can support a negative charge there, but what really makes it stable is now, so we can draw, so thinking about our electrons, so now we can kind of move this double bond here, and then that'll force a negative charge on one of the points. But then, right, we can kind of keep moving this negative charge around such that it's stabilized by the whole molecule, right? So this is one form of it here. Sorry, try not to screw up my double bonds, and then move it around. And so now it's at the other position. Negative charge. Right, so basically we're showing we can move this negative charge all the way around the ring here, which just really helps to further stabilize this structure. And so because, again, right, this negative charge is not only spread across the oxygen, but across this whole delocalized pi system, that allows it to function as a weak acid. I'll add weak acid there. If I remember correctly, its pKa was like somewhere in the 10 range, so pretty weak, but still significant. Oh, sorry. This is... I lost my note page. There we go. And so let's try another. Let's do a few naming practices. So let's try this one. So do we have guesses for this one? Yeah, so ortho, bromo, phenyl. Excellent. And of course, you could have also called it 2-bromophenyl, right? Same thing. So again, that's where, right, multiple names for the same compound come up. I think those are the main variations. And so this is used a lot synthetically. Most people like it at the 2 position for reasons of making pincer compounds, but you could also, again, do the meta position or para across, so 3 or 4, again, used interchangeably. Let's try another one. Let's see if you can figure this one out. I think its name comes out a little funny, but so question from the chat, yeah, the extra stick, you can identify it as a methyl group. So that's a good piece. So again, you're just kind of trying to piece the puzzle, put the pieces of the puzzle together. So that was good to recognize. And so that's probably kind of like the easiest way to name it by our IUPAC system. Right, so we have, again, methanol there, and then this is our phenyl group. So we can name it phenyl methanol then. That's completely appropriate for the IUPAC name. That being said, it has a common name. Again, just to confuse everybody. So this is commonly known as benzyl alcohol. But again, proper IUPAC name. So that was good. Again, just breaking it down, identifying the groups on there, and putting the name together. So let's look at 2 more kind of alcohol naming variations, especially with these weird phenyl groups. So try this one and then compare it to this structure down here. So what's similar, what's different about the name? Kind of identify the groups hanging off of it again. So what'd you notice about this chain here? How long was it?
So 5 chain.
And double check, because it should just be 1, 2, 3, 4.
You don't count the carbon in the benzene.
No, so this is, we can just think about this as our phenyl group here. And so chat has an answer that I like. And so they assigned it. And so again, alcohol should get the first priority. So it goes back to oxygen has a higher molecular weight than a carbon. So 1, 2, 3, 4. And then 4 carbon chain. And so then we can name it 4 phenyl, 1 butanol. And then how is this one different? So take a minute or so. And so what changed from this one to this bottom one?
On 2 instead of 1.
So 2 instead of 1, good. So 1, 2, 3, 4. So excellent. So then that makes it 4 phenyl, 2 butanol. Excellent. Questions about kind of the naming so far? All right, so this is probably a good spot to take a little 10-minute break. So then let's take our break and we'll continue with our reactivity. All right, so now we're going to look at reactions that these alcohols can do. And so something that they can do is we can deprotonate them. So right, using a strong reducing agent here, so sodium, potassium. Then you can form what's called your methoxide, or basically right, your charged group here. So deprotonate it, leaves it with our negative charge, and then obviously sodium is acting as our counter ion, or whatever we picked, right, if we had picked potassium. And so these are just useful reagents in organic chemistry. So they can go on to react. I'll say tert-butyl lithium was another famous one. So this is a reagent that is pretty potent. So it's flammable, pyrophoric, and it was famous for starting that incident that I always tell you all about, the horror story of the person who got lit on fire. So pretty reactive, potentially. And so then looking at other reactions and how to classify them. So a lot of these can undergo oxidation, or at least primary and secondary alcohols can undergo oxidation. And so looking at this reaction, so this is also called an acid catalyzed dehydration. So now we're removing water, right? So we lose our alcohol group and then hydrogen on the other side. So we lose that across, right, to make our double bond then and make our alkene. And so if we look at this, so we can see that a primary alcohol has two spots to undergo oxidation. And so we'll look at the products of this. So oxidation 2 times. And then a secondary alcohol can only undergo 1 oxidation. And so we can see that. So we're trying to think of the mechanism of what's going on. So right, you're trying to lose the hydrogen. And so of course in our primary alcohol we have 2 hydrogens to lose. Now in our secondary alcohol we just have 1, so it can only undergo 1 oxidation. And then this is the distinguishing factor is then, right, you have a tertiary alcohol, so carbon, right, that's attached to no hydrogens. So that's what we mean by tertiary. So no hydrogens. And so that means, right, there's no hydrogen to undergo elimination with this OH, right? So we cannot do the dehydration reaction, so it cannot undergo oxidation. So I don't know if this is something you might have covered in your biology class, potentially, of trying to distinguish between primary, secondary, and tertiary alcohols. It's like a pretty common. There's a couple of different tests to distinguish them with various oxidants. So I don't know if you've done that.
For the 1-propanol, can you highlight how there's 2 hydrogens that come off of it?
Yeah, so we'll keep going in the notes here. So we have that laid out. So this is our 1-propanol here. And so again, right, this is a typical strong oxidant. Like I said, I don't know if you've done this in your bio classes. but I might have expected that you might have. I can try to dig around and look for a demo on Thursday. I have to see what we have. There's different tests. And so, okay, we have our strong oxidant. So then you were asking, how do we do it? So of course, right, first dehydration. We form our double bond here and lose one hydrogen. And so, right, maybe star this. So now we're saying that a primary alcohol becomes an aldehyde. So, okay, we have our aldehyde group there. And so then we can take our aldehyde. Let me see where it is. Might be later in our notes. Sorry, because I want to answer your question, so I don't have it right here. I think it's on our next page of notes. So then on the next page of notes here, so looking at our second step of our transformations, now we have an aldehyde group from our primary alcohol, right? So we still have our hydrogen here, and so then it can undergo another oxidation reaction. So as kind of highlighted here as well, so right, permanganate is another oxidizing agent, and this allows us to remove our hydrogen and then make some sort of carboxylic acid there.
So the first step is the formation of the aldehyde group, and then the second step of the aldehyde group is losing that second hydrogen.
Yeah, to form the carboxylic acid there. So yeah, multi-step there. And so depending, so like I said, there's like a few different tests. So this would be like a way to test between like primary and secondary alcohols, right? So whether it can continue with a second oxidation. So again, a primary alcohol should undergo 2 oxidation steps. And again, just kind of showing typical strong oxidant reactions like permanganate or the dichromate solution. So both of those should be appropriate to take the aldehyde.
Can you go back to that first equation, the 1-propanol? Or
yeah, so then we're just focusing on here. So yeah, forming the double bond, right, kicks off one of the hydrogens and then leaving us with the aldehyde. So I didn't show the mechanism.
So does that hydrogen become aqueous?
Yeah, so again, right, I didn't go through kind of the aqueous workup of that. Yeah, we could, if you really want to get into the mechanism, we could. I was just trying to emphasize, right, so the primary takeaway is that the alcohol can undergo 2, or the primary alcohol can undergo 2 oxidations, the secondary alcohol can do 1, and the tertiary none. So that's the takeaway, but yeah, I'm more than happy to get into the mechanism later or something.
Just not working it now.
Yeah, because there's all these things of like aqueous workup, and that's where you do like protonation, deprotonation formally, mechanistically. So then, again, just general formula. And so now we're looking at, right, our secondary alcohol here, as shown. So it just has 1 H. So now we want to write secondary alcohol. And so, of course, instead of making the aldehyde, then it would make the ketone compared to the primary. And so again, showing the product here. So eliminated, make our double bond. Again, forming our ketone. And so no hydrogens attached to it, right? So now we can't do another oxidation with it. And so again, you could perform tests, there'd be distinct colors. There's several different oxidizing agents. Like I said, I just have to dig around in our chem closet. And so I'll just write it out. So again, just to emphasize that if we have our tertiary alcohol with no hydrogen to eliminate, and then this symbol is just an oxidant. And so again, write no hydrogen to leave, so no reaction there. And so now we'll again practice our naming, so a lot of naming. And so for our aldehyde nomenclature, so just like before, we'll look at our parent alkane chain, and then the E becomes an al, and these are often, I feel like, awkward to pronounce, and a lot of these aldehydes have common names anyways, but again, we'll just practice our IUPAC naming convention. And typically we try to give it the number 1 position, especially since it should be right at one of the terminal ends from our definition of an aldehyde. And so usually we don't include the number. And so we'll look at our common names and when we add aldehyde. And so we'll see what this means too when we have a CHO functional group attached to our ring. So that's, like I said, it'll be easier once we look at some examples. So then we'll start off with some simple ones. So again, counting our carbons. So this is 1, 2 there. And so this is ethanal. Again, kind of awkward. And that being said, its common name is acetaldehyde, for our acetyl group. So acetaldehyde, 1, 2, 3, 4. So then what's this one's name? How many carbons are in there? So how many carbons do we count in here? And make sure you include that one. 5. So excellent. So we have 5 carbons, we just have an aldehyde. So now this is pentanol with, again, an AL. And again, I don't know why all these aldehydes have common names, but this is valoraldehyde. Yeah. But like I said, you see, I never see the weird AL ending. You never really see it in practice. You see all these other common names. I'm not really sure why that is. I feel like some of this is historical, especially because we'll get to it, but a lot of these aldehydes are the basis of esters. So I have this page pulled up so we can get some context of what I'm talking about. But basically you put together an aldehyde and carboxylic acid to make what are called these esters, which smell nice. So like, I always think of Laffy Taffy when I start talking about artificial esters, like especially that really artificial banana smell of the Laffy Taffy. So yeah, like I said, I don't know why they have all these weird names, but I kind of think that's where it's from historically. So like I said, a lot of these are used to make lots of flavoring. All right, so let's keep looking at naming these. So let's see. So it makes this comment here where substituent positions are shown with Greek letters. And so let's look at what this means. So there are other ways to kind of prioritize these, which again, I think just makes it confusing, but so if we have something, so I'll put a chlorine group on here. And so what it means by this is we can describe our position in relation to this aldehyde. So one away is known as our alpha position, or of course it could be 2, right? So of course this is 1, so we said aldehyde gets a priority of 1. So this is 2 or alpha, 3 beta, or 4 gamma. So kind of confusing. So then I guess let's work through this one together. So again, find our longest chain. So 1, 2, 3, 4, 5. So we're at pentanol. And then we have to identify our groups, right? So this could be, we want to go 1, 2. Sorry, let me find another color. So we could go 1, 2, 3, 4, 5. So if we go that way, this could be 2-chloropentanol. Or if we want to follow this alpha beta gamma convention, which it mentioned is another possibility, this could be alpha chloropentanol. Or if you want some more variations, so this is 1, 2, 3, 4, 5, which is, remember, this base is valeraldehyde. So other alternative names could be alpha chloro valeraldehyde, or of course 2-chlorovaleraldehyde, all right. So I think those are most of the IUPAC variations of how you can write this one. And again, these alpha, beta, gamma, that's just by definition for these aldehydes. And so let's see if you can name one of these funky ones then. Sorry, 1, 2. I just don't want to miscount. All right, try to name this one. So do we get some guesses for the name here?
2-methyl-butanol.
2-methyl-butanol. So 1, 2, 3, 4. I like your butane. But then, so we have to give priority though to the aldehyde, right? So 1, 2, 3, 4. So probably not 2-methyl, but
3-methyl-butanol.
excellent. So 3-methyl-butanol. That weird AL ending. Questions on this one? And technically, right, we could have done alpha beta. So it could have been beta methyl butanol.
So the alcohols have a priority.
Yeah.
There are other like different priorities when you're going through like this naming scheme, or you're really not going to see like the alcohol.
I mean, you might. That's where you might get like discrepancies, because like, what if you have an aldehyde and a carboxylic acid? You know, it's like probably the carboxylic acid to take priority, but again, like that's also kind of the point of what we're saying is like people will come up with a different name if they assign the priority like a little differently, and then we're kind of seeing like it's all accepted, right? You look at Wikipedia and all these are like, these are the alternative names, and so it's like all these variations. But again, I think it makes it confusing, which is where the CAS number kind of helps us make sure we're all on the same page. But that's the difficulty of learning OCHEM too, is like you have the IUPAC nomenclature and then everybody has all these common names, so you're like learning almost like two different naming systems.
Is it commonly tested for both IUPAC and
Usually they just test on like the IUPAC.
Okay.
Although, I mean, you never know. OCHEM professors are always known as like the crazy ones. So now let's try some of those ones where it's talking about this carbaldehyde. So this is an example of that. So we have, right, our cyclohexane ring here. And so that's our name is cyclohexane and then carbaldehyde. And so then we could practice doing a variation of it. So now if I redraw this, but add a methyl group here. So see if you can think of what the name might be. So do we have guesses for this one?
4-methyl cyclohexane carbaldehyde.
I would just go with 1, 2, 3 methyl, but otherwise, I like your
So
name.
a carbon group in between, I guess it's part of the carbaldehyde, huh? So
Ye-
you just start after that.
Yeah, because it's kind of weird because, right, you're assigning this the first priority, right? So then it's like where it's attached.
Okay.
And then, yeah, so then it'd be 1, 2, 3. So yeah, 3-methyl then. And then we can still do the rest. So cyclohexane, carbaldehyde. And so yeah, there was a little methyl group. You know, people in the chat were having trouble seeing that. And so then ketone naming is, now we change our E to own. And so again, right, we have our substituent groups plus our ketone again. And just like before, you know, to confuse you, many of these simple ketones have common names, so such as propanone, that's acetone, and I've never really heard of anyone call it propanone. And so, okay, so this is just the aldehydes over here, right? Aldehydes, just keeping it straight for our notes. So that's those examples. And so now comparing that to our ketones on this side. And so, again, there's a lot of different ways to name these ketones, which we'll kind of go through. So we have, sometimes what people do is like they split them into their little parts, is what I say. So if we look at this example, so there's, like I mentioned, few ways to look at it. So we can either find our full carbon chain here. So this is 1, 2, 3, 4 carbons. And then, right, by definition, the ketone cannot be in the end, right? The aldehyde is on the end. So the ketone has to be on that second carbon there. And so we could either call it butanone based off of the 4 carbon chain. And again, the fact that it has to be at this 2 position, because it doesn't matter, right, either way. Or the other way to name it is people kind of, I see it as splitting off our 2 parts. So we have this ethyl group, and then methyl group, and then we have an ethyl group and a ketone, right? So then it's called methyl ethyl ketone. Same thing with this one. So looking at pentanone, right, we had to specify the 2 position because it could have also been at the 3, right, as shown right below it. So, okay, we had to specify 2. And we could have called it 2-pentanone, right? So 1, 2, 3, 4, 5 to again go with our longest carbon chain. Or splitting it into the 2 halves, so we have a methyl group and a propyl group. So methyl propyl ketone is another appropriate name. And so again, just comparing 3-pentanone, or you have 2 ethyl groups on either side, so diethyl ketone is also appropriate.
Are the parentheses still in IUPAC naming scheme, or is it another naming scheme?
I think that's probably like the more unofficial name, but again, it's like, I think I see this one used a lot more for, like I said, probably historical reasons of the ester synthesis, but not entirely sure where these naming conventions come from. And so then we can break down this one. So again, right, we have to follow our same procedures of finding our longest chain. So 1, 2, 3, doesn't matter which way we go. 4, so that gives us our bute. And I mean, I don't think that we really needed to specify that it was 2, because it really can't go at another position. And then we do need to specify our methyl group, so 3-methyl, 2-butanone. We could have also named it something else. So what was this group again? Anybody remember?
Isopropyl.
Yeah. So then we could name it, so then we have, so there's our isopropyl group. And so we could have also named it methyl isopropyl ketone, or probably isopropyl methyl to go in order. So isopropyl methyl ketone would have been another appropriate alternative name.
So because we're dealing with a ketone, the naming scheme, like the 2-butanone, that comes after the substituent group because we're working with the ketone.
Yeah, like the butanone comes at the end, yeah. So let's try, I'll have you guys try some. Now, let's see, 1, 2, 3. So see if you can name this one drawn. So do we have 1 guess or 2 guesses for names for this one? So 3-hexanone I think sounds good. So right, 1, 2, 3, 4, 5, 6. So there's our hexanone, and then we did have to specify it, so that's excellent there. Other names, so what would be the other alternative? So find your 2 halves there.
Ethyl propyl ketone.
Excellent. So right ethyl group, so ethyl propyl ketone is correct. All right, let's look at some other kind of weird ones. And so now what happens when we have more than 1 ketone? This is All right, so now we're looking at this kind of mess here. And so of course, right, we have competing aldehydes and ketone groups. So we still want to give the aldehyde the priority in this case, since, right, aldehyde by definition has to be at the end from the hydrogen. So, okay, we can at least start with that. So 1, 2, 3, 4, 5. So I'm just figuring out how long my chain is too. And so now, going back to our naming, so if our aldehyde is dominating, then we have our pentanal framework for our 5. And so then we just have to name these ketones appropriately. And then what's kind of weird is once you get multiple of them in a molecule, you can also refer to them as oxo groups. And so that's how you name this one. So now we have 3, 4, and then there's 2 of them, so dioxo, and then pentanol. So that one is kind of a strange one.
Is there an example where you skipped using the carbon in the aldehyde group as your number 1? Just like 2 examples in there or something?
So it depends, like, let's see what you're referring to.
Yeah, I think it was that one, because I started my carbon count at the carbon, oxygen, hydrogen bond. I started 1 there.
Yeah.
Here you're not, but in another one you are starting it at that.
So it kind of like depends on the framework, right? So in this case, the aldehyde is kind of more stuck on to what we're considering our primary chain here, right? So our longest chain is our cyclohexane, and so that's kind of our group, right? So that's why we assigned, and then it's kind of funny, right? So now we're looking at where the carbaldehyde or the aldehyde is attached to, right? So I'm not counting it. I'm just saying that it's on the first position of the cyclohexane. Does that kind of make sense? Versus this one where it's right part of the full chain. Yeah, so it's like, it's a little different. So yeah, it'd be,
Just kind of different priority naming or priority grouping.
yeah, because like I said, here it's kind of more considered like it's attached on there as like a substituent versus here where it's like part of the primary chain there.
Okay.
But again, like it doesn't make naming easy. So then we can we'll look at more examples. So if we just have 2 groups here, and so usually it's called oxo as well when you're like competing with like the aldehyde or a carboxylic acid. But then in this case, so now we have 1, 2, 3, 4, 5. So 5 carbon chain, and then again, priority doesn't matter in this case. So 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5 gives us 2, 4 pentane, and then dione. So now when it's, again, when you don't have any other competing groups and it's just ketones, you can use the dione there.
Would you consider this a cis molecule versus a trans molecule?
Not in this case because we don't have a double bond. So remember, it's that double bond that prevents the rotation and keeps it locked in either, yeah, this cis or trans isomer. Because this would have rotational freedom around this single bond. So other things to think about as you prepare for OChem is like, does it have rotational freedom around this single bond? You know, that's important versus a locked in double bond. Or triple bond, obviously, but. See if you can guess what this one's name might be. So any guesses for this one? So I like it. But yeah, this is one of those, so since we don't have any competing groups, we don't need to use oxo. So cyclopentanone is good. I know, to keep everyone confused and on their toes here.
That's because this is still a ketone.
Yeah, so we don't have, like I said, there's no other aldehydes or no other groups. And so then let's look at a few others. So we'll practice. So try these three out. So let's try this one.
Four bromo pentanone. Is that a flat line at the bottom, or is that a...
It was supposed to be a 6, but yeah, I drew it kind of, I'll admit I drew it poorly. So hexanone, let me kind of draw it so it's a better shape. Excellent, hexanone. Good. What about this one? So this one is 5-membered now.
2 bromo cyclopentanone.
Excellent. So 2-bromo cyclopentanone. And then any guesses for this one?
4-oxo cyclohexanone.
So 1,4, yeah, and then cyclohexane dione there. So yeah, we don't need to use the oxo since there's no like I said, no other competing groups, which is kind of confusing. Let's try some more ketone naming.
And it's diam because
Yeah,
there's
two.
no other groups on it too.
Yeah, correct. Because otherwise we would do the oxo, but there's no other competing groups, so we can just stick to dione. So let's try some other ones. So kind of mixed practice. So back to some aldehydes, if I can draw this out. So let's try that variation versus this one. So then what do we find was our longest chain on this one?
4.
So 4. And then what do we have for our name? So of course this is butanal here. And then what do we need for the rest of it? So what position is our hydroxy group on?
4 all.
Yep. So 4 hydroxy. Oops, if I could spell. 4 hydroxybutanol. Butanal. And then this one, we just added an extra methyl group. And so again, trying to go in alphabetical order. So then 4 hydroxy. Man, I can't put that X in there. 4 hydroxy, 3 methyl for our methyl group. So 1, 2, 3. So 3 methyl and still butanal again. So 1, 2, 3, 4 there. All right, we probably will have to stop there in the interest of time. So I think we need to finish up a few more probably ketone examples. So we'll practice a few more of that. And just seeing where we're headed. So right, we'll look at carboxylic acids as well. And some more reactivities. So again, just trying to name these different acids. And I'll try to bring in some demos too. So I promise you at least the Tollens test, and so that's the mirror reaction. But otherwise, I'll see what I can dig out with the alcohols. All right, so I look forward to seeing y'all in lab. And again, let me know if you have questions, especially with the poster and paper, so get help with that. And then any other questions on stream before I end this?